This is our complex ion. Before we draw anything, we can identify a few things just by looking at the compound alone. First, we can find the oxidation state of the metal cobalt. This helps us determine how many electrons are in the d orbital. In this case, cobalt is 3+. Therefore, it has 6 electrons in the d orbital. Next, we can find the coordination number. The coordination number is the number of atoms attached to the metal. In this case, there are 6 ammonias attached to the cobalt, therefore the coordination number is 6. Since we know the coordination number, we can also figure out the shape, which would be octahedral. Octahedral has 6 ligands attached. Lastly, we'll determine if the ligand is strong or weak. According to the chart below, ammonia is located here. Therefore, ammonia is a strong field ligand. Using the information we gathered, we will draw the valence bond theory diagram. First, we will start with the ground state. Since it is cobalt 3+, we will have 6 d electrons. Now, before we hybridize, we have to create an excited state. Since we have a strong field ligand, the splitting energy will be large. However, electrons want to save energy, so they will pair up. Now that the electrons are paired, we will hybridize the next 6 orbitals, creating a bonded state. The bonded state will give us 6 paired electrons, while the hybridized state would give us 6 sigma ammonia bonds. The shape of the hybridization would be D2sp3. And since we use 2 3d orbitals, it will be an inner d orbital complex. Now we will draw the crystal field theory diagram. Crystal field diagram describes the split of the d orbital, so it should match with the d orbitals from the valence bond theory diagram. Looking back at our compound, we know it has a strong field ligand. Because of this, there is a large repulsion between the ligands, electrons, and the d electrons of cobalt. This results in a large crystal field split. The lower energy level is 2Tg and the higher energy is Eg. 2Tg contains dxy, dyz, and dxz, while Eg contains dx squared minus y squared and dz squared orbitals. Since it is a large split, when we are filling up the orbitals, we must pair the electrons before moving on to the higher energy level. Now that we have filled out the orbitals, we can confirm it is correct since it matches the valence bond theory diagram. We can also identify other things looking at this diagram. For example, the pairing energy is less than splitting energy. If the splitting energy was less than the pairing energy, there would be greater stability by keeping the electrons unpaired. We also know that it is low spin because there are no unpaired electrons. Low spin is caused by the ligands and has minimal amount of unpaired electrons. And since it is all paired, we can also confirm that it is diamagnetic rather than paramagnetic, which has unpaired electrons.